In this next series of lectures, we'll be seeing what distributed file systems look like. In today's lecture, we're going to look at what the file system abstraction is, and we'll look at a design for a vanilla distributed file system. In the next lecture, we'll look at a couple of real distributed file systems. So what is a file system? A file system, as many of you know and have used in your real life, contains files and it contains directories. Sometimes the directories are known as folders. Essentially, files contain data. They might be your programs, they might be text, they might be executable files, and there might be a variety of other kinds of files. And the directories, of course, contain many files inside of them. Files and directories which are provided by the file system give a higher level of abstraction, and this enables users and processes to think about data stored in files and directories rather than forcing users and processes to think about the disk blocks where the files and directories are stored. That would be very uncomfortable, right? I mean, if you were thinking of what are the disk blocks on which my particular programming assignment or my particular videos are stored, that would be kind of an uncomfortable lower level of abstraction. Here, the file system provides you a higher level of abstraction so that you're able to think about user-centric aspects, and processes are also able to think about files rather than dealing with low-level details. So a typical file may consist of the following components. It consists of a header, and then it consists of the blocks. Typically, the blocks are of the same size because the file system imposes a maximum size on the block. The block size might be a few megabytes. That's typical, but of course it varies from file system to another. Those blocks, block 0 through block n minus 1 shown over here, contain the actual data for the file itself. So if you have a text file, then your actual text will be contained in these blocks. The header in turn contains a lot of meta information about the file. For instance, it may contain timestamps. When was the time when this file was created? That's a creation timestamp. That would include the date and the time at which the file was created. When was the file last read? So whenever the file is read by any process, the read timestamp is updated. When was the file last written is maintained in the write timestamp similarly. And finally, when was the header last updated? If the header was last updated at some time, then that time and date is written in the header timestamp. Now, of course, these are only samples. There might be other kinds of timestamps in the actual file systems themselves. Next, the header contains what kind of a file this is. So it may contain information about whether this is a program file like a .c or a .java, or whether it's a text file like a .text or a .doc, or whether it's an executable file like a .exe or even an object file like .o. This is useful for processes that are opening this file to know what kind of a file it is. Next, you have ownership. Who is the actual owner of this file? Which is the user, what is the user ID of the user who actually owns this file right now? The owner may not be the only one who can access this file. There might be other users who are allowed to access the file in different modes. Some users may be allowed to write the file. Other users may be allowed to only read but not write the file. And that is maintained in the access control list. The access control list maintains a list of all the users who are allowed to access this file. And for each user, it maintains information about which modes this user is allowed to access this file in. Is it a read-only mode? Is it a read-write mode? Is it a write-only mode? Or is it an executable mode or something else? Finally, you have the reference count in the header. This is an important integer that is maintained in the header. The reference count refers to how many directories contain this particular file. By default, when you create a file inside a directory, the reference count is set to 1. This means that this file is contained in one directory. However, you could hard link the same file from other directories, and this would increment the reference count. When you delete a file, the reference count goes down by 1. You'll see this when we discuss the API soon. But essentially, when the reference count reaches 0, you can delete the file. Okay? But by default, the reference count is 1, and it's incremented whenever you hard link the file. So what about directories? We have discussed files so far, but directories are just treated like files by the file system. Instead of containing data, however, the directories contain information about the files that are there in the directories. The directories don't actually contain the files themselves that are inside them. Instead, they contain pointers on disk, for instance, to the files, so that when you list the directory, it gives you the names and meta information about the files, but also from the directory itself, you can access those files on disk itself. So for most of our discussion, we'll be focusing only on files because directories are only a special case of files. So let's discuss what happens in the Unix file system, which is one of the more classical file systems, and a lot of today's file systems are based off of the Unix file system. The Unix file system uses a notion of file descriptors. A file descriptor is essentially a handle for a process to access, that is, read or write a file. Each process needs to open the file and obtain a file descriptor before it executes any operations on it. And then after it is done executing the operations, it needs to close the file descriptor. Whenever a file is opened by a process, the operating system creates an internal data structure for that file descriptor. So it creates a new file descriptor, creates an internal data structure, and then returns a handle to the process. Then the handle can be used by the process for subsequent read and write operations. So for instance, in a typical Unix system or Unix-like system, the process might call open to open a given file that already exists in the system with the file name and in a particular mode. The mode might specify that it's a read mode, or it's a write mode, or it's a read-write mode, both are allowed to, or it's an executable mode, or some combination of these three. This call goes to the operating system, which is running the file system, and then the operating system returns a handle, which is a file descriptor. Typically, the file descriptor is just an integer, which when passed to the file system itself, or the operating system, tells it what is the internal data structure to access. If the file doesn't exist in the system, then you can call create on the file itself, and that will again return a file descriptor after creating the file. Then you can do your reads and writes, and finally when you're done, when the process is done with all its operations on the file, it can close the file descriptor. This does not delete the file. This only closes that file descriptor and says to the operating system or to the file system that this particular process is done with its operations on this file for now. So essentially, the open or create opens a session where a process reads a file, and the close closes that session for reading and writing the file. So how do you read and write the file? Well, once you have the file descriptor, after you have called open or create, you can use the file descriptor as an argument in your read call. So a process, once it has opened a file, may call read on that file descriptor with an internal buffer specified and the number of bytes that it wants to read. Well, this call doesn't really specify where in the file you start reading from. Well, that is done by maintaining a read-write pointer as a part of the file descriptor. So the file descriptor, which is maintained internally inside the file system, maintains a read-write pointer, which is pointing to an offset within the file. Typically, the offset is initially 0 by default, but when you call a read with a num byte set to some value, say 10, right, the read will start reading from the beginning of the file in the beginning, because the read-write pointer points to the beginning of the file, and then returns, it returns the first 10 bytes, because num bytes is 10, into the buffer, the internal buffer of the process. But then after the read is done, the read-write pointer is automatically advanced by num bytes. So the read-write pointer now points to the 11th byte in the file. A subsequent read done to the same file descriptor will start from the 11th byte onwards. Okay, so there is an implicit read-write pointer involved here, so that processes do not need to deal with explicitly saying where in the file they want to read from. The same thing is true for writes as well. When you call write on a file descriptor with a buffer that says what you want to write in the file, and the number of bytes that says how many bytes do you want to write, again the write starts from the read-write pointer that is currently pointing to some offset in the file. After the write is done, the read-write pointer is advanced by num bytes. Now, the read-write pointer is kind of convenient because the processes do not now need to deal with explicitly saying where you are in the file, but sometimes you may need to do so. You may need to actually locate your file descriptor read-write pointer in a file, and that's where lseek comes into play. With lseek, you can take a file descriptor and you can say that you want it to point to a particular offset within a file. Okay, so this resets the read-write pointer to that offset within a file. This offset may be an absolute offset. You may say 10 here and say absolute here for whence, in which case the read-write pointer will point to the 10th byte of the file. Or you may say the offset is 10 and whence is relative, in which case the read-write pointer is advanced by 10 compared to where it is now. So that's a relative advancement, or a relative lseek. A few more operations that are useful. These are control operations: link, unlink, and stat. So remember, I mentioned hard linking in the beginning of this lecture. Well, here is where linking and unlinking can be done. So you can link a file that is at an old link to a new link by specifying these as parameters. This does not remove the file from the old link. Instead, it creates a new link that also points to the file. Okay? So it creates a new link at the second argument pointing to the file at the first argument. It does not duplicate the file, it just creates a new pointer inside the file system. Now, essentially, you'll have, after this link returns, you're going to have two different directories pointing to the same file that is located on disk. And in this case, these old link and new link are Unix style names, and so the directories actually point to those files. Whenever you call link, this is hard linking here, it increments the reference count of the file because the reference count refers to how many directories contain the file. This is known as hard linking, and there is a different kind of linking known as soft linking or symbolic linking, which does not affect reference counts. When you soft link or symbolic link a file, essentially you're creating a separate file that contains a pointer inside of that file to the file that you're linking to. When you delete the original file, the symbolic file stays on. It may refer to junk on the file system, but it stays on because it does not affect the reference count itself. When you want to unlink a file, remove it from a directory, you call unlink on the link, and this decrements the reference count. So if you link the file originally and its reference count was 2, you can now unlink it from one of the old links, and the reference count will go down to 1. The file will not be deleted. The file will still stay around with a reference count of 1 with the directory, with one of the directories pointing to it. When you unlink the file from the second directory that it was contained in, then the reference count goes down to 0, and now that file can be deleted. Finally, you can use these functions known as stat and fstat on the file name to get information from the header, such as the timestamps and the reference counts, into a buffer in the process itself. Now, these API functions that I've discussed are only the tip of the iceberg. Unix supports a variety of other APIs and API functions, and if you're interested in them, you should look them up. So what about distributed file systems? So far we have discussed a case where the client process that is accessing the file system is using the same operating system as the file system itself, and the file system was running inside the OS. What happens when you have clients running on different machines and on different OSs than the server, which is running on a different OS? Well, the files are stored on a server machine in these cases. The client machine, or the client process rather, does RPCs, or remote procedure calls, to the server machine or the server process in order to perform operations on the file. We'll see this played out in more detail over the next few slides, but what do we desire from a distributed file system? Well, we desire a few properties. First, we desire transparency. Transparency essentially says that a client process should be able to access DFS files, distributed system files, as if they were indistinguishable from local, say, Unix files. Okay? So accessing a distributed file located in a DFS should be no different from accessing a local file. In other words, the API should be the same. In other words, the code that the client uses to access a local file should be the same as the code that the client uses to access the remote file. Also, the distributed file system may be changing the location of the file. For instance, if the server is changed, it may be replicating the file for fault tolerance. It may be storing multiple copies of the file on different servers, and all of this should be invisible to the client. The client processes should not need to be able to know about where the file is located, whether or not the file is replicated, in order to access the file and do reads and writes on it. Next, you want to support concurrent clients. So the whole one of the bigger reasons to have a distributed file system is to allow multiple clients to concurrently or simultaneously read and write a file. Okay? And so you want a DFS to support concurrent clients. And finally, you want to have replication for fault tolerance. You may want to replicate the file or certain blocks of the file across different servers, so that if some servers fail, you don't lose the file. You still have at least one copy of the file around. So when you have replication or concurrent accesses, once again, there's a couple of semantics that you need to worry about. The first is one copy update semantics. This essentially says that when a file is replicated, its contents as visible to clients are no different from when the file has exactly one replica. Okay, so essentially this is saying that even though the file is replicated, as far as the client operations are concerned, the end result is the same as if the file had exactly one copy and was not replicated at all. Since you have RPCs going on in between the client, each of the clients and the server, you need to choose the semantics of your RPCs. You might remember from our discussion of RPCs earlier in the course that RPCs may have semantics. At least once operation semantics were the two common cases that we discussed. You need to choose which of these you use for your file system very carefully. If you choose at most once for a particular operation, you need to make sure that those operations are not repeated. For instance, append operations are okay with at most once because then those are not repeated. Right? You don't want to repeat appending the same piece of information to a file multiple times. However, some operations can be repeated multiple times without any side effects, even though they are repeated multiple times. These are known as idempotent operations. For instance, reading a file at an absolute position or an absolute offset within the file is an idempotent operation, and no matter whether you do it one time or a million times, you're going to return the same result as long as the file doesn't change. So operations that are idempotent can be used with at least once semantics. Next, you need to worry about security. When you have a distributed file system, your messages are going to cross over the network, and this means that attackers might be able to intercept and modify your messages. And so you need to make sure that two properties are satisfied. They are authentication and authorization. Authentication essentially says that the server is convinced that the client process is acting on behalf of the user that in fact it is claiming to act on behalf of. Okay, so this essentially authenticates the client process. After a user is authenticated or after a client process is authenticated, you need to verify that that user or that client process is actually allowed to access the file and perform operations in a legal manner. Okay, if the process is trying to read the file, then the process should actually be authorized to read that file. In fact, it should be present in the access control lists of that file. If it's trying to write the file, then it should actually have permission to write that file. So how do you maintain these permissions? Well, there's two popular flavors for maintaining these permissions. They are ACLs, or access control lists, and capability lists. One is the inverse of the other. The access control lists maintain on a per file basis the list of allowed users who are allowed to access that file, and for each user what mode it is allowed to access that file in. For Unix-like DFS's distributed file systems, typically the mode is read, write, execute, or some combination thereof. But for other distributed file systems, you could have other access modes allowed as well. But essentially, access control lists are per file lists of users and their allowed access modes. Capability list is the inverse, which is a per user list, and on a per user basis, it specifies the list of files and directories, if necessary, that that particular user is allowed to access, and for each of those files, what mode or what modes that user is allowed to access those files in. Now, capability lists are often split up into capabilities. Each capability would specify, for instance, for a pair of user comma file, whether that user is allowed to access that file and what mode it is allowed to access it in. If there is not a capability for a particular user file pair, then essentially that user is not allowed any access to that file. Okay, so now you know what access control lists mean, or what ACLs mean, and what capabilities mean. These are fairly commonly used terms in distributed file systems, and in general whenever security is being talked of in distributed systems. Next, let's build a distributed file system. We'll call it our vanilla distributed file system, or a vanilla DFS. The vanilla DFS runs on a server, and it also runs at multiple clients. It consists of three types of processes, two of them running at the server, one running at the client. At the server, you run the flat file service and the directory service. The directory service uses the flat file service. In other words, it's a client of the flat file service, even though it's running on the server machine. And the client service runs at each of the clients, and it talks to the directory service and the flat file service. Essentially, the flat file service stores files without worrying about their hierarchical structure. The Unix files and also Windows files, Mac files, all these file systems have a hierarchical structure for their files. The flat file service does not worry about the hierarchical structure. It simply takes the file IDs into account. The hierarchical structure is put into the directory service itself. So let's look at what the flat file services API looks like. So you can read a file by providing it the file ID. This is a unique ID of the file. Specify a buffer into which you want to read. You can specify the position in the file from which you want to read. This is the actual absolute position in the file. And you want to specify the number of bytes that you want to read. So this reads num bytes from the absolute position in the file, which has the file ID, into the buffer in the process's address space. Now, a few things to note here. File ID is not a file descriptor. There is no notion of file descriptors in our vanilla DFS. Okay? The file ID is a unique ID of that file. It's not a file name, it's a unique ID, and you obtain that ID by using the file name from the directory service, as you'll see soon. The other thing to notice is that we are using an absolute position in the file. We're not using an automatic read-write pointer. Why not? Well, because you're using RPCs here, you want to support at least once semantics, and you want this operation to be idempotent. You don't want this operation to be repeated multiple times and cause side effects. If you were using an automatic read-write pointer, then at least one semantics would just not sit well with this particular with the distributed file system, and so you don't want to use automatic read-write pointers. You want the operation to be repeatable without any side effects, and that's why you want to do a read at an absolute position. So this operation, the read operation that I've specified here at the top of the slide, can be repeated multiple times, and it will result in the same end effects without causing any extra side effects. Second, we don't use file descriptors. Why not? Well, essentially we want the servers to be stateless. We don't want to maintain any information on the server side, including any data structures like file descriptors, because the server might crash. If the server crashes, we don't want to lose any data and leave the server in an inconsistent state. We want the server to be able to recover from where it left off without using any state from the previous incarnation. Okay, so keeping the server stateless makes it easier to recover the server after failures because there is no state to restore. So in contrast, as we have discussed, the Unix single machine operating system file system is neither idempotent nor is it stateless. Writes are done similarly from an absolute position to an absolute position in a file. They have the same semantics as a read. You can also create or delete a file with a given file ID, and you can get or set the attributes of that file ID using a buffer. What about a directory service? A directory service allows you to obtain a file ID for a given file in a given directory using the file name. This directory would be the /delimited hierarchical name of that directory within which that file is located. Then after you locate this file ID, you can then use this file ID in the flat file service that we already discussed to then execute operations on the file. You can also add a name to a particular directory with a given file name, and this increments the reference count. You can also unname a particular file name in a given directory. This decrements the reference count. If it reaches 0, then the server can then delete that file. For a given directory, you can also get the list of all files that match a given pattern. This is kind of like ls-al or dir in Windows, followed by a grep in Unix or a find in Windows. Okay, so that's our vanilla distributed file system. In the next lecture, we're going to see the design of two very popular distributed file systems that continue to be used today. They are NFS and AFS.